Ferroelectricity. This presentation is about ferroelectricity. What are ferroelectrics? Ferroelectrics are certain dielectric materials that collectively have spontaneous electric polarization. This means that the material can be electrically polarized or have an electric dipole moment without an external electric field, and the polarization can be switched in ferroelectric materials. Their molecules each carries electric dipole moments, which collectively and spontaneously align to form a polarized material very similar to this. This is the concept of ferromagnetism and ferromagnets, which we commonly just call magnets, just like how a bar magnet has a magnetic field. A ferroelectric material has an electric dipole moment, where one is positively charged and the other negatively charged. A good example of a material whose molecules have dipole moments but is not ferroelectric is water. In a water molecule, since the oxygen atom is slightly negative and the hydrogen atoms are slightly positive, this produces a net molecular dipole moment. However, the molecular dipole moments of every molecule in water don't spontaneously align, so water is not polarized. A prototypical material whose molecular dipole moments do align and is ferroelectric is lead titanate. Lead titanate has a non-centrosymmetric crystal structure. This because its ferroelectric properties arise from displacement of the titanium atom from its oxygen-oxytocin sensor, as can be seen in figure A. The off-center titanium atom is positively charged, which results in a net dipole moment for the crystal cell-oriented downward. To lead titanate's crystal structure, the crystal cell's dipoles are oriented in the same direction, which makes lead titanate ferroelectric. The direction of charge can also be switched if an electric field is applied. In the direction of P, the titanium atom would be attracted upward to point, resulting in a reverse dipole moment. This process carries up to larger scales of the material so through. This method of the polarization of the entire material can be switched above lead titanate's ferroelectric transition. Temperature T, the crystal structure is deformed and the titanium atom becomes placed in the center of the cell. The charges of all of the atoms then cancel out and there is no longer dipole moment or net polarization of the material. Also, it can be polarized if an electric field is applied. This behavior demonstrates the paraelectric property. There are a few key differences between ferroelectricity and paraelectricity. Figure A, when an electric field is applied to ferroelectric material, it becomes polarized and the crystal structure of the material is permanently deformed, even after the field returns to zero, leaving a remnant polarization. This cycle will be talked about more later. On the other hand, in figure B, paraelectric materials can also be electrically polarized by applying an electric field. However, when the field removes the polarization of the material decreases back to zero. Returning to the diagram below, we see that about the transition. Temperature, the titanium atoms is in the center of the cell, no longer producing a net dipole moment. It can be moved by an electric field, but once the field is gone, it will return to its original position. This is the general reason why paraelectric materials have no remnant polarization. Real-life ferroelectric materials are more often than not inhomogeneous. These small areas with homogeneous, arranged spontaneous polarization are called domains. These domains are separated by domain walls. Domains and ferroelectrics range in size from only a few nanometers across to a micron. Even so, each domain has its own net spontaneous polarization. The polarization of all the domains may cancel out, and the material as a whole will not have a net ferroelectric polarization, as shown on the left. Here we can see our material with domains oriented in completely different directions. The ferroelectric domains can be aligned by applying an external electric field. On the right, all of the domains are aligned in the same direction, demonstrating a net polarization for the material. Next, let's look at ferroelectric behaviors here. The first picture we can see no net polarization. The second picture we can see net polarization. The x-axis is the applied electric field, and y-axis is the polarization of a sample ferroelectric material. We call this diagram the PE loop. A pristine ferro material has misaligned domains and therefore no net polarization, as can be seen at the center of the diagram. The arrows and the squares indicate direction of the net polarization in each domain as an electric field is applied. The domains within the material will begin to align in the opposite direction of the applied field. For example, if an electric field is oriented with positive upward, the negative ends of the domains will be attracted and the positive ends repelled, resulting in the domains aligning downward. Eventually, the material will consist of a signal domain and so cannot be polarized and further. Even if the electric field is strengthened, this is known as saturation polarization. As the electric field is removed, some of the domains may misalign. However, the material will remain polarized. The remaining polarization is called the remnant polarization, and the amount it decreased by is the non-remnant polarization. As a negative electric field is applied, the polarization will decrease and the total polarization will go back to zero. At this moment, the applied electric field is called the Kharkiv field. Continuing to strengthen the negative electric field, the domains will be aligned again, but in the opposite of direction. This process can be repeated. The polarization displaces high stresses with the external electric field. So this is called high stresses loop.